Hi all of you. Welcome to another lecture of nanoelectronics. Today we are going to learn two new topics, that is the quantum transport and the Coulomb blockade. Myself Maria Joseph, Assistant Professor in Electronics and Communication Engineering Department of MBC CET PD-MED, leading this session. These are the topics in Module 5 of KTU syllabus. The first topic for discussion is the quantum transport. Quantum transport occurs when the nanostructures are connected by an external current, to an external current by means of leads. That is, this occurs when we connect the nanostructures with the help of leads. In order to observe a quantum transport, the effective mass of the electrons should be small to guarantee high mobility. As we know, if the size is less, definitely the mobility will increase. Quantum transport is observed at high temperatures with a low electron effective mass. So, mass reduces at high temperatures and we can see that quantum transport can be observed. Since the dimensions of the nanostructures are very small as compared to the mean free path, the quantum transport occurs. Consider the figure. We have a small topic that is called the quantized conductance. Consider two reservoirs of electrons connected by a short quantum wire. Look, you can see it is connected by a short quantum wire and you have two leads here. The length of the wire is shorter than the electron mean free path in the material. Hence, there is no scattering and the transport is found to be ballistic. The leads are assumed to be ideal such that no scattering occurs in this case. Okay, that is, in ballistic conduction, no energy is dissipated in the conductor and there is no elastic scattering. What is the speciality of a ballistic conduction? In ballistic conduction, no energy is dissipated in the conductor and there is no elastic scattering. In the quantum transport, each conducting channel contributes a conductance of 7.746 into 10 raised to minus 5 Siemens. Understood? That is, we considered two reservoirs of electrons connected by a short quantum wire as shown in the figure. Then the length of the wire is shorter than the electron mean free path in the material. These are the conditions. In that condition, there is no scattering and the transport is found to be ballistic. Okay. We have a small topic, Landau formula. It is a formula for the total quantum conductance with two leads and many leads of the nanostructure. What occurs? It is a formula that is connecting some relationship between the quantum conductance with two leads and many leads of the nanostructures. If capital N is the total number of channels contributing to the conductance, the total conductance is given by G is equal to E square by H sigma Nm up to NTNm square, where the transmission probability is the TNm square. Capital N is in total number of channels. E 2E square by H. What do you mean? What is E square? That is of a single channel. That is, E is 1.6 10 raised to minus 19 and H is 6.6 into 10 raised to minus 34. So that will be the value of conductance in each channel. This is the expression for the quantum conductance for two lead with many channel mesoscopic system. That is, for many channels, this is of a single one and this is of total. And this expression is called the Landau formula. The next topic for discussion is the Coulomb blockade. Coulomb blockade is, or Coulomb charging, occurs when the total capacitance of the object is so small that by adding a single electron requires significant charging energy. That is, each electron becomes significant in this case. That is, when total capacitance of the object is so small that by adding a single electrons, you get significant charging energy. Okay, electronic discrete configuration permits one to pick up electric charge one electron at a time at specific voltage values. Nanoparticles of diameters less than 2 to 3 nanometer may exhibit this phenomenon. It is the basic building block of a single electron transistor. That is, discrete electronic configuration permits one to pick up electric charge one electron at a time at specific voltage values. Nanoparticles of diameters less than 2 to 3 nanometer may exhibit this phenomenon. It is the basic, that is, this is the basic building block of a single electron transistor. Now look at this figure. Let us consider a semiconductor quantum dot structure connected to two electron reservoirs as shown in the figure at each side by tunnel junctions. You can see by tunnel junctions. In order to allow the transport of electrons to or from the reservoirs, the barriers should be very thin. Okay. And this is the figure which shows the energies of the quantum dots when the number of electrons in the dots is changed. Okay, that is energy levels at specified voltages. That is this figure. Now, if the quantum dot is capital Q and its capacitance is given by capital C, then the potential energy is given by Q square by 2C. Therefore, we have the total potential energy is given by capital Q square by 2 into C. Therefore, energy of the at least E square by 2Z will have to be provided to the electron. And we can see that the voltage will have to be raised at nearly should be minus E by C or to E by C. That is, since the electron can either enter the dot or leave it, we can see that the electrons cannot tunnel if the voltage is less than E by 2Z. If the voltage is less than E by 2Z, then it will not allow the electrons to tunnel, which means we will not have current in this area. That is, hence there is a voltage range between minus E by C to plus E by C in which current cannot go through the dot, and hence the name Coulomb blockade. Okay, before that we had one point that we have left. That is, to add a single charge to a semiconductor or metal nanoparticle requires energy. Charging energy is independent of the materials, and it also has been observed that individual single wall carbon nanotubes. Okay, it can also be shown that even the change of one elementary charge in a small system has a measurable effect in the electrical and transport properties of the dot. That is, even the change of the smallest thing, smallest charge can cause a significant effect in the electrical and transport properties of the dot, and that phenomenon is said to be the Coulomb blockade. That is, this is a very important thing to be added when you are saying about Coulomb blockade. Fine. And this is the graph, and between this there is no possibility of current minus E by C2 plus E by C. Thank you.